try to follow all our social media platforms, and as it's been shown on the platform for this workshop, you will see the social media platforms there. Please like and comment and follow the social media platforms for more visibility, so that other people in your cycle can as well, people in your cycle can benefit from whatever we are doing in this place and in times to come. So we are going to be mathematical model development is the next thing we are having on agenda, and then please, it's going to be a time where he will be taking us through those steps. All right, thank you so much. Enjoy the ride.
Good afternoon, everyone. We are welcome back from our break. I hope you enjoyed the tea break. Did you enjoy it? Okay, did you enjoy the break? You removed the tea, like Mr. Idowu said. You removed the tea from the break. Did you enjoy the break or the tea? Which one of them? Or the two, both of them? Been having, like Prof said, that the objective, the goal of this symposium is to infect as many persons as possible with modeling skills. And I hope that before the end of this program, we would have been infected. We would have gotten a good grasp of modeling and the use of modeling in decision making. So quickly, we'll be looking at how to develop epidemiological models, developing mathematical epidemiological models, and at a point we'll be doing some group works. We'll be putting us into groups so that we can see how to develop models. Let's wait for media to slide mode. All right, thank you. Okay, so developing mathematical epidemiological models. So, like I said earlier, we want to see how to develop models, mathematical models that is used to make predictions, like Prof said earlier, and to to inform decisions. So before we go into that, we'll have a little recap of what compartmental models are. While Prof was addressing the question raised by one of the participants, he went through addressed some of the methods or ways of developing models. Now, compartmental models is based on into classes, different classes, according to the infectious status of individuals. So in this case, we'll be having three classes or three compartments. We have the susceptible individuals, the first class here, the susceptible individuals. We have those in the infected class, and we also have the removed or the recovered class. Now, who are the susceptibles? The susceptibles are those people that they don't have the pathogen in them. They are not yet infected, but they have the capability of getting infected. Do you get that? So the susceptibles are the people who don't have the disease at that particular point in time. Now we have the infected or the infectious individuals. These people that are in the infectious class, they have contracted the disease, they have the disease, and they can transmit the disease to others. That's the second class we have in this case. Now we also have the removed or the recovered class. Individuals in this class, they have gone through the disease, they had the disease, but then they have recovered from the disease. Or in this case, they have been removed from that infectious class It could be through death or through other, through whatever. And then they cannot be infected. For this particular model, the people in the recovered or the removed class, they can, after they recover from that disease, they cannot be reinfected. So these are the compartmental model we want to look at for now. Just a simple. Now, movement between compartments. How do people move from one compartment to the other? Those in class can progress and move to the infected class through what? Through transmission. When there is a transmission, when a susceptible person comes in contact with an infected class or the infectious class through transmission, and those in the infected class can progress through what? Through recovery. They can recover, or as in this case we said, they can die and leave that, and they move to the recovered or the removed compartment. Now, from compartmental models to differential equations, how do we move from compartmental models? Infected person, what happens? There is a transmission. So that S there, we can see the S there. Oh. Okay. Okay, so this S is susceptible, interacts. Can we go to the slide? Vidya. Okay. So this S is interacting with the I. The susceptible individual is interacting, so that there's an interaction. Susceptible, and that interaction is given by products. The interaction between S and I mathematically is described by product S times I. At this particular rate, beta, this is beta, this is gamma, so they can recover at this rate and move to the removed or recovered class. Now, the rate at which each compartment equations. Now, how do people move? How do people change? Now, if we take this hall as a population, for instance, how does the population of this hall, how does it change? How does this population change? It changes. Somebody just came in and there's an addition to the population of this hall. So the population is changing with respect to time. After some time, somebody leaves the population. So it changes when there is what? Change of a particular population or of a quantity. In mathematics, we describe the rate of change of a quantity using this. The Q, if you have a quantity mathematics, the Q, the T. So the rate at which the S, the T, the S and the susceptible individual interact with an infected individual at this particular rate, beta. Beta is the transmission rate. And beta is dependent on two terms. Beta is a function of, this is beta. Beta is equals to what? C times P. C is the number of contacts. The number of contacts that is made. And then probability, P is the probability that that contact leads to transmission. Now, if an infected person, if I'm susceptible and I have come in contact with an infected person, that's a contact. Not every contact leads to transmission. Do we agree with that? Not every contact leads to transmission. So there is a probability. Given a contact, what is the probability that there will be transmission? And so beta, the transmission rate, is determined by, or is a function of the number of contacts times the probability of transmission given a contact. So beta, transmission rate is given by that. Now, can we return to the slide? So we said the rate at which S changes with respect to time is given by minus beta Si. Minus because the susceptible population is depleting with respect to time. If you see the table here, this box, rate of change equals to what? Inflow minus what? Outflow. Can we see it? It's not too clear. Rate of change equals inflow minus outflow. So if you look at the susceptible population, what is the inflow into this susceptible class? What's the inflow here? The inflow is what? What is entering into the susceptible population? Who is talking? Can we chorus it? What is entering into the susceptible class? Nothing. So the inflow is what? The inflow is 0. The inflow here is 0. Nothing is entering into the susceptible class. We will see why later on. What is the outflow? Is there an outflow to the susceptible population? Look at our arrow. So this term here is describing the number of cases that are leaving this, the number of cases leaving this susceptible class, and then they are moving into this class. So there is an outflow from the susceptible population. And so the inflow, we said, is 0 minus the outflow. The outflow is given by beta Si. Now, this, as they are leaving, this number or proportion is leaving the susceptible class, they are entering into where? The infected class. So just like Prof said earlier, susceptible, the loss of susceptible is the gain for the infected. Just like when somebody dies, we say that what? Earth's loss is what? Is heaven's gain. So susceptible loss is what? Infected gain. So these guys that are leaving the susceptible compartment, they are leaving and then they are entering into this place, into the infected compartments. So we have beta Si here minus, so we have inflow here minus the outflow. How are people leaving this infected class? We mentioned it earlier. Through what? Through recovery. People leave this place. So how does the infected class, how does the infected population change with respect to time? When there is addition here, which is given by beta Si, and then there is removal through this. And so we also have the recovered class. The recovered change in this format. When people recover, when they leave the infected class, they move into this class. Is that clear? So, and this is a system of differential equations. We have 3 equations here. This is a differential equation, and then the third differential equation. These 3 gives us a system of differential equations with initial conditions. So it's called an IVP, just like Prof explained earlier while he was addressing that question. So we have the initial population of susceptible is greater than 0, strictly greater than 0. The infected class too at initial time also strictly greater than 0. Then the recovered, we assume that at that initial state there is no recovered class. Nobody has recovered. Is that clear? So, and the total population is given as this. N equals to what? S plus I plus R. So we have divided the total population into 3 classes. Into the susceptible class, into the infected, and the recovered class, according to individuals' infection status. Now the term beta I, let's go back to that place. This term, beta I, beta times I, is called the force of infection. It is defined as the rate at which susceptible individuals get infected. The rate at which susceptible individuals, they get infected, and it is denoted by lambda. Usually in mathematical modeling, we denote that by lambda. So lambda, this is lambda. For those of us that are not mathematically inclined, this is lambda, it's a Greek letter, equals to beta I. So this is the force of infection. Now this term, beta Si, let's go back there again. This term, beta Si, is known as the incidence. Beta Si is the incidence. What is incidence? In epidemiology, what is incidence? Incidence. Who will help us? Media. What is incidence? New cases. Incidence. What does it mean when we say incidence? What is incidence in epidemiology? Incidence is the number of new cases. What about prevalence? What is prevalence? Huh? Old plus new. Incidence is the number of new cases per unit time at a particular time. Prevalence is the total number of cases at a particular time. So prevalence is old cases plus, if you remember during COVID-19 pandemic, NCDC will publish the number every day. They will give us, this is this number for today. The next day they publish the number. That is incidence, the number of new cases at a particular time. Yes, somebody has a question. Media, you want to help us? Somebody is raising her hand. She wants to ask. Please. Can you? This is mic. Okay, the slide. Media. Can we have the slide?
Okay, so my question is, the susceptible individuals, are they the entire population or a subset of the population?
Okay, the susceptible is just a subset of the population. So we have divided the entire population into groups. So initially, just like COVID-19, during COVID-19, before we had an index case, nobody was infected. So we can say everybody is susceptible until we had an index case in Nigeria, and that person was the only person in the infected compartment. So before you know it, the disease began to progress, and people from the susceptible population began to get infected, and then they begin to move to the infected class. So the susceptible population is not the entire population, it's a subset. Is a class or a subclass of the entire population. It's not. I don't know if you get the explanation.
I get that, we would have, at the instance where there is no case at all.
Yes.
Is that population a susceptible population?
Yes, we can say it's a susceptible population. If there is no case at all, there is no disease, no transmission. So although there are some populations, it is not everybody that is susceptible to a disease. It is possible that in the population, for example, if we introduce a disease into this place, everybody might not be susceptible to that disease. But what is that we might assume that, okay, at that point where there is no disease, we can assume that everybody is susceptible. Then when an infection is introduced into the population, we now say, okay, so we now have the susceptible population and then the infected population.
So at each point,
yes,
we can make an assumption, one, that the entire population is the susceptible population.
No. We can't, because we are looking at a disease or an infection. Now, if we are talking about a disease or epidemiology, we will understand that already there is an infection at time T. If there is no infection, if there is no disease, then we are not talking about that disease in the population. But once there is a disease in the population, then we now start
and discuss it in the absence of any disease or
at all.
So now I understand that when there is a disease, then in this susceptible population are those who are prone to be infected with that disease.
Exactly.
That would mean a subset of the population, right?
Yes.
Thank you, sir.
You're welcome. So just like we mentioned earlier, the susceptible, they don't have the pathogen in them, but they have the capacity they are vulnerable. They can catch the disease, but they don't have the disease in them at that point in time. So now we're talking about so we said the incidence is what? We said incidence is new cases, and prevalence is what? The total number of cases at a particular time. So and we also said prevalence is old cases plus new cases. Now, so the incidence, this term, beta SI, captures our incidence. You know, when Prof was saying, he was explaining, he said, when you look at a particular disease, you now find a mathematics mathematically is represented by beta SI. So beta SI is our incidence. What about our prevalence? What mathematical term there is representing our prevalence? What's our prevalence there? Quickly, we have limited time. The prevalence is what? The prevalence, what term there? Or what quantity is representing prevalence? The what? DS over gamma I? No, that's not our prevalence. Our prevalence is what? I. This is the prevalence. This guy here. The total number of cases at a particular time. So this guy represents my prevalence, while this guy represents our incidence. So beta SI is referred to as incidence, the number of new cases. And in maths modeling, we have two most frequently used incidence function. We have the mass action incidence and the standard incidence. The mass action incidence is given as that beta SI. This guy is the mass action from the mass action in chemistry. I think we had a chemist there. Yes, mass action. The idea is from chemistry. So beta SI. So it is assumed that every susceptible comes in contact with every infected individuals at this transmission rate beta. So this is a mass action incidence. Now it's also known as density dependent transmission. The mass action incidence is also called density dependent transmission. The contact rate depends on the density of the population. That is, the more infected people around, the more it is likely to catch the disease. The more infected people around, the more it is likely for you to catch the disease. So it is density dependent. It depends on the more people you have in the population, the more it is to catch. So we have the mass action incidence, also called the density dependent transmission. This is one of the incidence functions used commonly in modeling. Now every infectious, and it is suitable for modeling small populations, maybe a class. In a class now, a classroom of say 30 or 50 students, we can assume that everybody comes into contact with one another, is it not? So the mass action incidence is suitable for small population, is valid, is realistic for small populations, e.g. a classroom. While given as beta S I over N, it is also known as frequency dependent transmission. So the contact rate depends on the frequency of contacts and not necessarily on the density. For instance, HIV. If we have, say, there are people with HIV here now, it does not depend on the number of persons. For me to get the disease, it does not depend on the number of people with HIV here. What does it depend on? It depends on the frequency of my contact with them, except if it is maybe there is a sex orgy, and then everybody is having sex with one another. Then you can say it is depending on density. But diseases such as sexually transmitted disease, STDs, does not matter how many people around you have STDs. It only matters how many of them you have sex with. So it is called frequency dependent because it depends on the number of contacts and not on the density, just like mass action. And it is usually suitable for large populations, unlike mass action, which is used to model very small populations like the classroom. Now we want to talk about model assumptions. Model assumptions. Yes. Influenza, Lassa fever.
Now, the population, you understand? The population you have determines the kind of transmission pattern you follow. Now, for mass action, is density dependent in terms of you need to have maybe large number of infected people. But for this other one, even with one infected mosquito, a lot of people can get malaria here. You don't need to have many mosquitoes to get malaria. once it can bite you, you can get malaria and all that. But now, in a small population, just like a classroom, you understand? Like you said, so you have that kind of density-dependent population defined of a transmission pattern you follow. Yeah, no, as in more people who are infected in a small population. Yeah, yes.
Okay, sir, thank you. I have limited time, so I'll be fast. So, to model real-life systems, real-life system is complex. And so we need to be able to model them effectively. We need to have some simplifying assumptions. Assumptions help us to simplify our models. They are the set of simplifying rules or conditions that are used to represent complex dynamics of disease transmission. They help to simplify complex real-world dynamics to make the models tractable. Now, every model is limited by its assumptions. Okay? I'm trying to be, I have limited time. These guys. Okay, so now in the SIR model above, we formulated an SIR model. We have made some simplifying assumptions. Because to model a disease, a real-world problem, is quite complex. So be able to make it tractable, we have given some simplifying assumptions. Now, one of the first assumptions we made for that SIR model above is that the population is closed with no births, no deaths, and no migration. Remember when we were looking at the differential equation earlier, we mentioned that the inflow is what? The inflow is what? We said the inflow is 0 because we have made an assumption that for that particular model, there is no birth, there is no death, and there is no migration. And this makes sense for epidemic disease that happen within a short period of time. You can assume because the period is short and demographic factors like death, birth, and migration might not have much effect on the disease dynamic. So we can decide to ignore such factors as death, birth, or migration. So for that SIR model, we have made that assumption that it's a closed population. We have also made an assumption that infected individuals become infectious immediately after infection. Immediately they get infected, they become infectious. In real life, it does not always happen like that. There is a bitten by mosquito. You do not become infectious immediately. It takes some time, some days, about 10 to 15 days before you start. But for this model, we have assumed that immediately the person gets infected, it becomes what? Infectious and start transmitting the disease. And that is why from the S class, once there was a contact and transmission is established, people move from S to where? To the I class. We've also assumed that there's homogeneous mixing. Every individual have equal probability of coming into contact with any other individual in the population. And for this model also, we have assumed that individuals acquire permanent immunity after recovery and they cannot be reinfected. Once you recover from this model, the SIR model we are looking at, you can no longer become susceptible. You have recovered for life. You can no longer catch the disease. And this is suitable for diseases like what? Are there diseases like that when you recover, you don't catch the disease again? Like measles, chickenpox, smallpox. There are diseases like that when you recover, you are not susceptible again. And then we also assume that transition rates are constant and they do not change over time. The rates, for instance, from S to I and then from I to R, we've assumed that they are constant and they do not change over time. Now, this is a simple SIR model and we have listed all these assumptions and many more. Now, we need to be able to model reality effectively, we need to relax some of these assumptions. Do we get that? Because in reality, some of these do not hold. So we have to relax some of these assumptions and we need to put in more complexity into our model. And so we can relax some of the assumptions above to make the model more realistic. If we relax the first assumption says that the population is closed. No births, no deaths, no migration. But here now, I have a model where the first assumption has been relaxed. So we have births now. People are coming in now. We now have inflow. The first one, inflow was what? 0. Here, people are coming in through what? Through births. And then people are also dying naturally. Natural deaths could be maybe through accident or any other cause of death. So we have relaxed the first assumption, and then we now have an SIR model with demography. Now we can also relax the second. If we relax the second assumption or the first two assumptions, what does the second assumption says? It says infected individuals become what? Infectious immediately after infection, and they remain infectious until they recover. We want to relax that assumption. We want to remove it so that our model will be able to capture reality more. So if we do that, if we relax the first two assumptions, we have this model. We now have the exposed or the pre-infectious individuals. Initially, we had just 3 classes. Now we have added complexity. We now have 4 classes where we have the exposed or the latent period, people in the latent class. When a susceptible individual comes in contact with an infected individual, the person does not immediately become infectious. There is a lag. There is a latent period. And so the people in that compartment, we created a compartment for that, to capture that. So as you relax the assumptions of a model, your model becomes more realistic. It becomes more complex. But it should not be too complex, because if it becomes too complex, you cannot what? It is difficult to be difficult to track. So we have gotten those 2 equations. Now we want to see how to develop models. How do we develop models? Compartmental models. So we'll be doing this together. Now, just like Prof said, a key step in developing models is understanding the biology of that disease. If you don't have a good understanding of the biology of the disease, your model will be wrong. If you don't understand the biology of COVID-19, for instance, how is COVID-19 being transmitted? And then, or of malaria, you don't understand that malaria is caused by infectious female anopheles mosquitoes. And then you just put a model that does not capture that. It is a wrong model. So the first step is that what? You must understand the biology of that disease you want to model. That's a key step in mathematical modeling. So let's go through the natural history of COVID-19 infection. Let's see some of those things we know about COVID-19 infection. It is an infectious disease caused by the SARS-CoV-2 virus. How does it spread? What is the mode of transmission of COVID-19? By what? Maybe through contact with people, or you touch a contaminated object, you can get infected. We have the symptoms of COVID-19. Incubation period. What's the incubation period of COVID-19? It's between 2 to 14 days. What is incubation period? What is incubation period? The period between when you get exposed to the disease and you start showing symptoms, is it not? And then the latent period for COVID-19 is about 5 days. Do we have asymptomatic infection for COVID-19? Are there asymptomatic infection? Those that they have the disease, they are infectious, but they are not showing symptoms. We have that for COVID-19. What about recovery? Does recovery confer lifelong immunity for COVID-19? When you recover from COVID-19, can you get reinfected again? Yes, unlike the first SIR model we saw, like measles. When you recover, the chance that you will get infected is slim, almost zero. But for COVID-19, you can still get infected after recovery. So we need to get all these facts about any disease you want to model. Those are things you will now put in your model to capture or to respond to any question you are trying to answer. Does COVID-19 lead to death? It can cause deaths. So having some of these facts or the natural history of COVID-19, we can now develop compartmental models of COVID-19. So I've developed a simple compartmental model for COVID-19. So this is a simple compartmental model. We have the susceptible individuals, and then this is lambda, capital lambda. People are coming through this. It's called recruitment rates. Could be either through birth or through migration. Now this is the force of infection. The rate at which susceptible people become infected. Now, we have the exposed class, we have the asymptomatic class, we have people that are symptomatic, and then we have recovered humans. Now, when a susceptible person, how can a susceptible individual get infected? If he comes in contact with either, if a susceptible person comes in contact with either asymptomatic person or a symptomatic person, that person can get infected with COVID-19. And that's what is captured here. I is the symptomatic, A is the asymptomatic. But for COVID-19, studies have shown us that the infectivity rate of the asymptomatic is lower, is less than that of symptomatic individuals. And that's why we have a parameter here, sigma. It's called modification parameter. It's less than 1. It captures the fact that asymptomatic individuals are less infectious than the symptomatic. So this is the force of infection, beta I, and then A over the total population. This is the standard incidence, just like we mentioned. So when this interaction happens, people move from susceptible, they move to the exposed class. For COVID-19, we said it's about 5 days. So that period when you are not showing symptoms, you are not transmitting the disease, you are not yet infectious, but you are infected already. Now, those in this class, a proportion of people in this exposed class can either become asymptomatic or they become symptomatic. 1 minus K become asymptomatic at this rate rho. Another proportion K becomes symptomatic. And after some time, people naturally recover from COVID-19. In fact, most people do not need treatments to recover from COVID-19. We have limited time. Okay, my time is up. We are supposed to have group work. I don't know if we'll still be able to have that. Now, so that's that for COVID-19. Now, also malaria model. We have some little facts about malaria too. What's the mode of transmission of malaria? How is malaria being transmitted? When a mosquito bites a human and then injects the sporozoites into the bloodstream, the person gets the disease. Or a susceptible mosquito can also get the disease, can also get the parasite from an infectious woman. Do you know that? So that's the mode of transmission. The latency period, when a mosquito, an infectious female Anopheles mosquito, ingests or injects sporozoites into the bloodstream, the person does not immediately become infectious. It takes time. That's the parasite goes through some stages. We have the liver stage, we have the blood stage, and then the gametocyte stage. So those periods before the person becomes infectious takes about 10 to 15 days. And so we need to capture that in our model. What is the most vulnerable population for malaria? We mentioned that earlier. Does recovery confer lifelong immunity for malaria? Once you recover from malaria, you don't get the disease again. Yes or no? No. You can get reinfected again. Can it lead to death? Can malaria lead to death? Yes. A lot of people are dying from malaria. So these are some of the facts we need to understand about the design model. So some of these things are captured in this malaria model. So see the malaria model. Can we go to the slide, media? So we have, this is the human population. We have the human population, and then we also have the mosquito or the vector population. So these are the human population represented by subscript H, and then we have the mosquito population. Because of our time, I won't be able to go through some of this. So that is that on developing mathematical models. I don't know if we'll be able to go to the group work. Maybe will it still be possible, or we postpone it till tomorrow or some other time? Or we should attend to questions now? Okay. It's okay. All right, thank you. So we have some group exercise, but we won't be doing it today because of our time. We'll be looking at them first thing tomorrow. We'll be dividing ourselves into groups, compartments, but this time around it is not based on our infectious status. Models, developing some of these models, develop a COVID-19 model that incorporates 2 pharmaceutical interventions. We can also develop that incorporates 2 non-pharmaceutical interventions. What are pharmaceutical interventions and non-pharmaceutical interventions? MPIs and PIs. Can we give examples of PIs, pharmaceutical interventions, and then non-pharmaceutical interventions? Examples of this for COVID-19. Yes, sir. Face mask, non-pharmaceutical. Social distancing, vaccine, treatment. So all those interventions can be captured. They can be incorporated into your model. Just like Paul said earlier, you want to model the effects. How effective are these interventions in controlling COVID-19? So we may want to see how to incorporate such interventions into our models. Now we also develop a model that incorporates LLIN and vaccination. LLIN is long-lasting insecticidal treated net. That's for malaria, and also for that for malaria. So by God's grace, we'll be grouping ourselves tomorrow and looking at some of these models. Thank you. Questions?
All right, so let's appreciate Mr. Ashon. He has taken us through how to develop mathematical epidemiological models, and particularly use it to come to reconvene tomorrow so that we can see how. So we want you to think about it. Please, let's help us project it. Media, help us project it. The questions. So go think about these questions. So when we come tomorrow, we'll put ourselves into groups. That's what we are starting with tomorrow by God's grace. He has shown us examples of some models, taking us through assumptions, and that led into that model. So now we are to work on this. So tomorrow we are going to start from this. So let's go and think about it. This way we are going to start from. So questions. Yeah, questions. So I give us number once you indicate to ask question. So 1
for the prevalence. So that is what I wanted to talk more about.
Okay. So we said in our for instance, we have DS. Okay, maybe we should go to the model. Let's go to the model. We have this guy. Model. Is it moving? So the incidence, we said the incidence is the number of new cases at a particular period in time. And we'll give an example of during COVID-19. We have NCDC publishes the number of new cases every day. And that incidence is mathematically is described as, for that model that we looked at, beta SI. This is the incidence. Mathematically, the number of new cases is represented as this function, beta SI. The susceptible individuals interacts, and that interaction mathematically is represented by the product of these two guys, at this particular rate. And we mentioned that beta is also a function of contact and probability of transmission given a contact. So this guy represents the number of new cases per unit time. Then the prevalence, we define prevalence as what? The total number of cases. Total number of cases at a particular time, or the old cases plus the new cases. The total number at that particular time. So, no, not the total number now. Yes, if it's all right. Yes, sir. So the total number at that particular time gives us the prevalence. So for this case now, the prevalence is, we said, is represented by I. What's I? I is the total, the people in the number of infected, the total number that are infected in the population. Mr. Gabriel, we have, this is S, this is I, and then this is R. So new cases are coming in. This is the population or the total number of people infected, which is the incidence, the prevalence. Total number of cases. This is the prevalence. Now, people, when this guy comes in contact with anybody here, a proportion of persons here are coming into this place. They are adding up. They are coming up. So at a particular time, the total number of infected persons or the total number of cases is called the prevalence. I don't know whether you got. Sorry, and let me say also that this is different from community. It's quite different. These are two different concepts.
Those are because I think I saw in the audience that it seems that somebody was saying, is it cumulative? This is not cumulative. The idea is this. Now, today, how many malaria cases do we have currently? That will be whatever it was yesterday, and the new persons that came down with it today. That's, as of today, that's the prevalence. The new cases will be those ones who came in newly, right? But now, cumulative incidence will be addition of all the new cases over time. That's necessarily from, for instance, from January till now, if you want to look at addition of all the new cases, you add up all the new cases together that came up down with malaria. It's not necessarily the same thing as the number of people who are with malaria today. The reason being that some of them would have recovered, some might have died due to, so when you take all of those ones, they are the ones that now form what you have currently. So that's the prevalence. What you have, new people today, new people, previous time, add up everything. That's cumulative incidence. So that's quite different from incidence or prevalence, as the case may be. That's why he kept on saying that it's the number of current, cases altogether. Old, that's why we say old and new. When we say old and new, that is people who had it before now, together with people who just had it. So currently, so when you have already taken away those that have recovered or that might have died due to the disease.
Is so enriching. I really learned a lot. My question is just straightforward. It's about the malaria model.
Okay.
I don't know if the presenter can please give an elaborate explanation on that model. I'm interested. All this, the symbol on K, what does this stand for?
Okay.
Yes.
All right.
You can just, because
okay.
You rushed over it because of time.
Media. So let's quickly
a kind of understanding.
Yes.
On how to do my assignment or classwork. Thank you.
Media. Okay, so this is the malaria model. These are susceptible individuals. A susceptible person, when it gets bitten, look at this. These are infectious mosquito. Can you see the infectious class, ma? This red class, the first one on the mosquito population. So and then look at the dashed lines. The dashed lines represents the interaction between infectious mosquito and susceptible humans. Thank you. So this is infectious mosquito beats a susceptible person with this force of infection here. Beta represents the biting rate, And then, B represents the biting rate. This beta is the transmission rate from mosquito to human. Beta MH, the transmission from mosquito to human. And then these are the infectious mosquito over the total population. So this gives that. Now, also susceptible mosquito. When a susceptible mosquito or infectious, a susceptible Anopheles mosquito takes blood either from an infectious, from an asymptomatic human or from a symptomatic human. Remember we mentioned that these two classes, they are infectious. Only that these guys, they are not showing symptoms. But these ones, they are showing symptoms. But both of them are infectious. In fact, in malaria, the asymptomatic individuals are the ones that are driving the dynamics, the transmission most, because they have the disease, they are transmitting it, but they don't even know that, and then they're not treating it. But if somebody is symptomatic, he goes to the hospital, he gets treated. But the asymptomatic, and that is why when we are modeling malaria, we need to capture, it is important to capture the asymptomatic population, because they drive malaria transmission dynamics the most. And so it is important to know that. So these guys, when a susceptible mosquito gets blood meal from this guy, it becomes infected, and then it moves to this place. And also, it can also, this guy can also what? Susceptible mosquitoes can also get, when it bites symptomatic humans, they can also get the parasites, and then they become infected. So it is not only mosquitoes or humans that are getting parasites from mosquitoes. Mosquitoes too can also get the parasites from humans too. Yes, if a susceptible mosquito, a naive mosquito, bites an infectious human, it can get that disease also, and that's what is happening here. That's what is happening through this arrow, this red arrow. So this one shows the interaction between the infectious mosquito and the susceptible humans. The interaction between the infectious human, they can also give mosquito the parasites. And that's what is happening here. And so we also have, now at this exposed stage, we mentioned that when mosquito bites the infectious Anopheles mosquito, female, bites a human, the person does not immediately become infectious. There are stages. There is the liver stage, the parasite or the sporozoites will undergo different stage. And so during that period, it takes about between 10 to 15 days. And so people in that period or in that stage are placed here. They are exposed. And that is why they are kept in this exposed class. After the duration of the exposed period, you either become asymptomatic at this particular proportion. 1 minus K proportion of the people move to this class. They become asymptomatic. Or they start showing symptoms and then they move to this class at this proportion. And so for malaria, I think the proportion of asymptomatic or symptomatic to asymptomatic is about 80 to 20%. So for every malaria cases, we have about 80% are asymptomatic and 20% are symptomatic. So we have this 1 minus K will become asymptomatic, and then K proportion K becomes symptomatic. And people, those in symptomatic class, they can die. This is the death-induced, malaria-induced death rate. So this delta is representing death due to malaria. This mu H, they are representing natural deaths. Everybody can die naturally. Whether you are susceptible, whether you are in infected class, you can die naturally. Any death that is not caused by malaria is termed natural death. It could be death by any other disease or death by anything, accidents or whatever. It's termed natural death. So these guys are the rates of natural deaths. Why this is captures the death due to the disease. And then those in the asymptomatic class, they can recover at this rate, alpha A. They recover at this rate and then they move to this class. The guys here too can also recover and they move to this class. Now, after some time, that you've recovered, people lose immunity. Unlike our SIR model, where we said it confers lifelong immunity. For malaria, malaria does not confer lifelong immunity. When you are infected and then you've recovered, you can also return and then become susceptible. You lose. So this omega here measures the rate at which people lose immunity, the rate of loss of immunity. So, and I hope it is clearer now. All right, thank you. Yes, the same process. This, we've captured it. Look at this. This is the force of infection. These are the symptomatic humans, the asymptomatic humans. And then this now, this beta is the transmission rate from human to mosquito. Remember, it is mosquito, the parasite now. These guys are giving mosquito. These guys are also giving. So these are the ones captured here. The A and then the I. And so that's it there. It's paradox.
Because if there is no infectious person, there won't be infectious mosquito. So where did malaria start? Is it from a particular animal or from where?
So it's like the chicken and egg problem, the chicken and egg paradox. Which one comes first? Is it the chicken or the egg? So it is. So, but I maybe Prof. I think probably it's from the mosquitoes first, but it's a question that it's a paradox that we can look into. Which one comes first? The chicken or the egg? Which one comes? So we can look at that in first. Is it the mosquito that has the disease first or human? So maybe we'll do.
All right. Last.
Thank you, Prof. Okay.
I realize that there is no control variable.
Okay.
So my question wanted to be on the control intervention. Okay. At what point do we infuse the control? But I realize that in your explanation you have not talked about control. So let me not be preemptive. Is that okay? Maybe when you continue the lecture,
yes,
next time I will now ask the question.
Yes, and you see that's one of our exercises that we're going to be looking at tomorrow, how to incorporate control interventions into models. How do you incorporate? And the next presentation will also capture some of those things. How you will see models that have control interventions. So by tomorrow we'll look at it. So for these models, they are just simple models without any form of interventions, without control measures. Thank you, Prof.
All right. So thank you so much, Mr. Shion. Please let's appreciate Mr. Shion for his presentation. Now, I told us that honestly, we are trying to see how to touch on a lot of things that we have scheduled for today. And the time is really not our friend today. So we'll try as much as possible to move. And let's see how far we can go. So I'm going to be calling on the next presenter who will be talking to us on. Now, Mr. Shion has laid another foundation of building models and all of that. Now, there are key things that are important for us to extract, information that are important for us to extract from that model, which will be of interest to public health guys, and extracting such information is very important, and we need to be able to learn how to go about it. One of such key quantity that the public health guys want to look at is what is called the reproduction number. And so I'll be calling on the next presenter, Dr. Abidemi Afis, who will be looking at how to compute reproduction number from models. All right, join me to welcome Dr. Abidemi Afis.
Yeah. Good afternoon, everyone. Yeah, I'm Afis Abidemi. I will be making a little extension to what the immediate previous facilitator have just worked on. So, and as it was being mentioned, whether we are doing quantitative or qualitative analysis of a model, there are some key things that are very important to whatever we are doing that will really give a lot of information to the policy maker. And one of such threshold quantity is reproduction number. So, next generation matrices also have different approaches, and in particular for this talk, we'll be looking at the Drich and the Wathmog approach to computing reproduction number using next generation matrix. So why is reproduction number so important to us? It's hungry. Okay. Okay. So like I was saying, the basic reproduction number is also called basic reproductive number or basic reproductive ratio, as the case may be, is the single most important parameter or threshold to leave out every other analysis of a model. One of the things you need to get is the reproduction number, because of the burden of a particular disease under investigation. And this threshold measures the average number of secondary infections by observing total lockdown, the use of face mask, and eventually when vaccine eventually came into place. By that time, if you want to look at this threshold, we will be talking about effective reproduction number. So in a well-mixed population, so if P is the fraction of the population that is effectively protected, then we have effective reproduction number to be 1 minus P R naught, where P is the proportion of people who have been partially protected. And with the use that, we can also look at the proportion of people that needs to be vaccinated. We can have before we can have the disease being eliminated in the population. Okay, so in order to compute this, like I compute the basic reproduction number of a. So in order to use the next generation approach, so this approach rests on the observation that are not characterized by regarding the infection transmission as producing infected individual. So going by the definition of the basic reproduction number, we said it's an average number of secondary cases that a particular infectious person we are looking at epidemic, because initially the epidemic will begin to grow, follow an exponential growth. Okay, when we have compartmental models of ordinary differential equation, where traits are taken into account in discrete categories, So it is important that one define a matrix that relates the number of newly infected individuals in the various categories in consecutive generations. Okay? So, and this particular matrix is called the next generation matrix, and this particular matrix was introduced by Diekman and Isenberg in 1990 as referenced in 1. The reproduction number R0 is then defined as the spectral radius of the next generation matrix. We see as this will be illustrated with some examples later. So we have several techniques that have been deployed to derive the next generation matrix from compartmental models. And this talk, like I said, will be focusing particularly on one of them. So, and this is the Van-der-Driesch and Wartburg approach. So this particular assists in a technique for the derivation of the next generation matrix from ordinary differential equation governing the dynamics of compartmental models for disease transmission. Okay? So we will divide the compartment into two broad categories in order to make use of a next generation matrix. Like we, okay, so I may not be able to directly be applied to all these examples, so we will get them clearer where we are applying the flow chart of the model being discussed earlier, and from that flow chart we have this system of equation given in 3 as the resulting ordinary differential equation coming from that model. If you look at each of these, what is coming in will take positive terms, and what is leaving that compartment will be negative. If you look at susceptible human, that population is being populated at a recruitment rate lambda. That's why we have lambda here. And then people are losing their immunity to join that class. We have omega RH join that class. So the rest goes that way. So we came up with this model. So where lambda is as defined this. So, and for a model to be well posed, we must have attached an initial condition. So this is the initial condition. As Prof asked the other time, we must have our S0 to be strictly greater than 0. Exposed individual can be greater than or equals to 0, and I of 0 must be greater than 0. A of 0 can be greater than or equals to 0, while R0 can also be greater than or equals to 0. So in order to network. So in order to apply the next generation matrix to compute the reproduction number associated with that model, we apply the next generation approach, and we record that system 3 as a unique disease-free equilibrium. Before we compute R0, one of the things we need to do is to find the disease-free equilibrium of the model. So at equilibrium, we will have the S dt to be equals to the E dt, and is equals to the I dt, which is also equals to the A dt, and is also equals to the R dt, and is equals to 0. So when we are looking at a steady state solution, we set this to be equals to 0. That means there is no variation in those variables. And one other thing we also do is that we will identify the infected compartment. And like I said the other time, E I, and A are all infected compartments. And we will set all these to be equals to 0. E will be equals to 0, A will be equals to 0, because at that time, there is no infection in the population. So when we do that to that model, we are going to have that the S dt will be lambda minus mu r. And this is equals to 0, because we have already set that rate to be equals to 0. By the time you substitute E equals I equals A equals 0 in every other equations, you will realize that all those equations will vanish. We are only left with the one corresponding to S. And when we solve this, we are going to get S star is equals to lambda over mu. So, and when we look at this, that means at disease-free equilibrium, thank you, sir. So it's lambda minus mu s. Thank you. So we have S star is equals to lambda over mu. And at disease-free equilibrium, when there is no intervention, the susceptible at steady state will coincide with N star. It will coincide with N star. You know, N star will be, N star is equals to S star plus E star plus I star plus A star plus R star, right? So we see that this is already 0, 0, 0, 0. So N star is equals to X star. So if we look at that, then that leads us to obtaining the disease-free equilibrium of the model as what we have in the slide. We have the disease-free equilibrium to be this. So the next thing is to identify the infected compartment. You remember that one of the techniques of next generation matrix is to group all the compartments into two categories, the infected and non-infected. So in this case, the infected compartments are E, I, and A. And we must also note the order. Note that order. We have EIA. Not that I'm putting A first. It must follow that order. Okay? So from there are two important matrices which are F and V. So the first one will give us a vector which is a vector of new infection. While the second one is the transfer terms, other terms. So I will. So the first thing is to identify the infected compartments like we did. We have E, I, and A. Then we want to put this. Let me say I have this to be X equals EAI. I want to put this system such that the X dt is equals to F minus V. I want to put it in this form, such that the X dt is equals to F minus V. So that means I'm going to have the E dt, the I dt, and the A dt equals so let's look at the model. We have lambda S minus rho plus mu E. So the new infection here is lambda S. That is the new infection there. That is the incidence term. So we have lambda S. Here we have lambda S. In the remaining compartment, we don't have new infection. So for this, it will be 0, 0. Minus the remaining term from E compartment is rho plus mu E. Rho plus mu E. So then for the high compartment, we don't have new infection there. Then looking at this, we are going to have alpha X, alpha S plus mu plus delta I minus kappa rho E. Then for the A compartment, I will have alpha A plus mu A minus 1 minus kappa rho E. So I will have this. That means my F will be this. Okay, call it F will be this component term, while the other term will be V. And when we look at that, we see that what I have here is exactly what we have here. So the next thing is to linearize this to get our transition matrices, which is now capital letter F and V. So to get capital letter F, we are going to differentiate. If I say this one is F1, F2, F3, derivative of each of these functions now with respect to E, with respect to I, and with respect to A. If I differentiate 0, 0, I will have 0 with respect to E, to E, to I, to A. This also 0, 0, 0. So I'm left to differentiating beta S into sigma A plus I over N. Over N. So, thank you, sir. Thank you, sir. Just leave this and this. So, if you look at this function, we see that we have a function N, which is not explicitly a function of time, but a function of S, E, yes, wrong that. S, E, A, I, and R. That means for me to differentiate this, I will make use of quotient rule. But I may decide not to go through that process in the sense that since I know that at disease-free equilibrium, my E, A, and I are what? Are zeros. So it will still give me as if I treat lambda N as a constant. Because you know in that population, why am I not treating N as a constant? Because the population I'm dealing with is not constant. And why is that population not constant? Rate of change of the total population with respect to T is not equals to 0. Because of the disease-induced death and the constant recruitment rate. Okay, so if I differentiate this with respect to E, what am I going to get? I will get 0. If I differentiate with respect to I, I'm going to have beta S over N. So I will have beta S star over N star. That is a disease-free state. So then differentiating with respect to A, I will have beta S star sigma over N star, right? So the next thing is to substitute S star and N star at disease-free state so that I will have my F to be 0. I said at disease-free state, S star and N star coincide. So I will have this one to be beta, while I have this to be beta sigma. Then I have 0, 0, 0, 0, 0. That is the F matrix. The next thing is to get the V matrix also. To get my V matrix, I will also do the differentiation of the V, call it V matrix vector there. So with respect to E, I will have rho plus mu. With respect to A, with respect to I is 0, with respect to A is also 0. So the second one, with respect to E, I will have minus kappa rho. Then with respect to I will have alpha S plus mu plus delta. Then with respect to A, I will have 0. Then the last one, with respect to E, is minus 1 minus kappa rho. Then with respect to I, it is 0. And with respect to A, is equals to alpha A plus mu. So one of the things that we must take note is that our V matrix must be invertible. That is, it must not be a non-singular matrix. it must be not be a singular matrix. It must be a non-singular matrix. So because the next generation matrix has FV inverse. That's the next generation matrix. It involves the inverse of V. And if V is invertible, that means that method will break down. Okay? So if we are able to get our V, the next thing is to find the V inverse, which we can easily do. So if we evaluate the V inverse, we are going to get what we have here. The next thing is to find the product of matrix F and the V inverse. If we do that, we are going to have the result that we have here. So going by this, we know by definition, which is one of the definitions there, the basic reproduction number is the principal eigenvectors of the next generation matrix V, dominant eigenvalue of that matrix. And going by that, we have a 3 by 3 FV inverse matrix. We expect how many eigenvalues? We expect 3. And out of these 3, we have 2 that are zeros. So why the remaining one is non-zero? And that non-zero coincides with the reproduction number associated with that model. Okay? So, like it was said the other time, that building a model has to do with the question we have in mind to answer. So maybe later we make that model to be a base model when there was no intervention at the early stage of COVID-19. But later we begin to use observed social distancing, wearing of face masks. So we may want to modify that model such that it will be able to capture those two interventions specifically. Wearing face mask and observing social distancing, they are two different measures, but they both target the same thing. What are they targeting? To reduce the contact. We want to reduce the number of contact that a susceptible person can have with an infected individual. So we specifically capture these two interventions by modifying the previous model to specifically capture social distancing and wearing face mask. And we let these two control interventions to be represented by epsilon S and epsilon F respectively. So since the two interventions are targeting the contact rate, then that means the intervention will focus on the force of infection. That's why we are attaching the two. We are attaching the two interventions to the force of infection. So if epsilon S is equals to 0, what happens? There will be full transmission, isn't it? And when epsilon S is equals to 1, or either of the two is equals to 1, what will happen? The force of infection will disappear. That means there will be no transmission. Then we said that there is 100% protection against the spread of the disease. So having the force of infection being modified, we can have a new model of that COVID-19. Then when we go through the process of getting the basic reproduction number we did the other time, here we will be talking about what? Is it still basic reproduction number? Effective reproduction number, because we are capturing two particular intervention. Okay, so if we do that, this is what we are going to get as our effective reproduction number, the first term there. And when we look at that and relate it with previous expression we have for the basic reproduction number, we will realize that this control factor is just a product of the R naught. And as such, we are able to express the effective reproduction number in terms of R naught. Now, at this point, I will ask a question. Is effective reproduction number greater than basic reproduction number, or the other way around? Which one is greater? Okay, so basic reproduction number is greater than effective reproduction number because of this reduction factor. We have this reduction factor here. Okay, so the other model we want to quickly also look at is that malaria model, which has been previously discussed extensively. So representing the same flow chart, so we want to derive the corresponding ordinary differential equation associated with this model. So from there, we come up from this system of ordinary differential equation governing the dynamics of malaria in the human population. This is for human population, susceptible human, exposed human, infected human, asymptomatic human, and recovered human. So and lambda H is as previously defined. We have this for the human population, and likewise we have for the mosquito population. So this for the mosquito population, bringing the two subsystems together, we have a full system governing the dynamics of malaria in the interacting human and mosquito population. So we have a system of differential equation governing the dynamics of malaria. So the first thing to do for us to be able to get the basic reproduction number, because there is no any control intervention, for us to get the basic reproduction number, we observe the infected compartments. In this model, what are the infected compartments now? Look at the human population. What are the infected compartments? Is it E? Okay, EH, IH, and AH. So we have three infected compartments from human population. Then from mosquito, how many infected compartments? We have two. We have EM and IM. So following that order, we have the order EH, IH, AH, EM, and IM. Right? So like I said, the first thing is to work on the disease-free equilibrium. If we follow the same approach, the disease-free equilibrium of that model will be SH star equals lambda H over mu H, and SM star is equals to lambda M over mu M, while other state will be 0 at a disease-free state. Okay, so we move on to compute F, calling F, and calling V using the same technique, so which I believe it is clear now. So from here we obtain the linearized matrix F and V from the calling matrix F and calling matrix V. So if we do that, we are going to get our F as steady state to be this, and by the time we substitute the S star and N we beta MH, because SH star coincide with NH star at disease-free state. So from there we have this, and similarly we are going to have our matrix V as we obtain it here. So what is the next step from here? We obtain what? So we obtain our V inverse. So from there we look for V inverse, which is obtained as this. So after obtaining the V inverse, we find the product of F and the V inverse matrix. So if we do that, we are going to get this. We are going to get FV inverse to be this. Okay? And lastly, we find the eigenvalues of the FV inverse matrix to be as we obtain here. So it is a 5 by 5 matrix. We expect 5 eigenvalues. And out of these 5, 3 are zeros, and 2 are additive inverse of one another. We have the first one being positive, the other one being negative. And if you take the magnitude of the two, the dominant will be the one with positive, and consequently our R naught is equals to what we have here. So that ends my talk. So thank you for listening.
All right, thank you so much, Dr. Afis. Now, I know this is a bit of mathematics that we have done. I know sometimes, like Prof said, he said the method is in the what? The method is in the what? Mathematics. Sometimes, and I'm happy that some people in public health are also here. There are some mathematical rigor that go on behind the scene of whatever results, is being presented, particularly if you have to do a kind of quantitative work. For instance, now, if Dr. Afis is going to be talking about what is the reproduction number of so disease now, you will not bug the public health guys with this thing. It will just tell you that it is so number. It will just tell you that this is what is happening, and you just see the number. But the approach of getting that reproduction number is what's, at least using one of the methods, of the various methods, is what he has taken us through. And I believe we enjoyed it. Did you enjoy it? Yes. So let's ask questions. After now, we'll be going for our lunch. And when we return, we'll return to do some hands-on with her programming lunch. But then before we go and launch, let's launch some questions. All right, questions. So just put up your hand as usual. I will give us numbers. Sir? Okay, so 1, 2, any other person? 3. Is that all? 1, 2, 3. Okay, in 4, in that order. Please, can you help me with the mic? Give them the mic.
Thank you for the lecture.
You're welcome, sir.
So precise. Please, I want to ask this question. The reproductive of reproduction number, when it is greater than 1, and when it is greater than 0, and when it's less than 0, you show us what it is. But when it is greater than 1, what does it mean?
When it is
equals to 1.
When it is equals to 1.
When it is equals to 0, Joe, you gave us 2 instances.
No, I said when it is greater than 1 and less than 1.
Okay, when it's greater than 1 and less than 1. What does when it is equals to 1?
So when
that
it is
not captured.
When it is equals to 1, that means the disease will still be in the population, but at a steady level. At a steady level. Yes, it will be stabilized. Yes, it will. So
it's not increasing. Either is it decreasing?
Yes. So, but maybe as we had this, it is not always the case that when R naught is less than 1, the disease will eventually die out in the population. There may be a situation whereby we observe bifurcation, particularly backward bifurcation. That may influence the coexistence of the 2 criteria, whereby we have R naught less than 1, but it is still saying that the disease is persisting in the population. So that's why some of this analysis is important when we are doing, even when it is even quantitative. If you are going by quantitative, that means we must be able to identify a particular parameter that is causing that. And then at what level will that parameter attain for us to be able to eliminate the phenomenon of backward bifurcation?
There is 0. You understand what I'm saying now? So COVID is not 0, it's not completely 0. It's there, but it's not causing havoc in terms of there is no spike.
Good, yeah.
Are you getting me now? But it's there in the population, and a lot of people, some people are asymptomatic, they are not showing symptoms, but at a low level. So that R naught for COVID may be 0.9. Take for instance, not up to 1. Does not mean that it's not there. It's there, but is not causing any major crisis that everybody can begin to run around and all that. So I think that's the issue about bifurcation stuff that is talking about.
Thank you, sir.
Yes, sir. Thank you very much for that insightful talk. I would like if you can help throw more light to that effective reproduction number. I'm more conversant with the basic reproduction number. You said it is the number of secondary infection an infected person can infect in the susceptible population. Now, for that effective reproduction number, just throw more light, and what inference can we deduce? What is the epidemiological meaning? Like, how do we apply it, and when do we need to calculate it? Thank you very much, sir.
Okay, so thank you. I think I've mentioned those two scenarios in the course of my presentation, that when you are to study the dynamics of a particular disease mathematically, as at when no intervention has put in place, if you want to know the burden of that disease, one of the thresholds you can compute is your R0. And in most cases, at the beginning of epidemic, people they estimate that from the data. So before they begin to use a more complex compartmental model, because when you are using a more complex model, it may be difficult to estimate that from data. Then that comes to other approaches like next generation techniques that I've just explained. So whatever you now get from that, it will mean that, for instance, if your R0 is 1.2, so to say, or 2 approximately, it means that when there is an index case, the person will be able to infect on average 2 people over the period of infectiousness of that particular person. The interpretation is also similar for the case of effective reproduction number. The only difference is that in that population, the population is not completely susceptible. There are some people that maybe they have been vaccinated. Do you understand? So because that there is now presence of some intervention, pharmaceutical or pharmaceutical intervention like vaccination. If there is vaccine, are immune. They are partially immune due to the vaccine they've taken. In fact, there will be a time we'll be talking about herd immunity. That how many percentage of the people do we need to even vaccinate before we can be able to attain R0 being RE less than 1. So that will take us to herd immunity. It is not always the case that every population must get vaccinated before we can achieve that target. So there may be disease effectually. I wouldn't know if that has answered your question. Okay. So when you look at maybe, okay, the slide is not there again. You know, you remember that I related effective reproduction number with R0, where I have 1 minus epsilon S times 1 minus. So we have the relationship between R0 and RE as 1 minus S times 1 minus epsilon V R0. Are we together? So we will have RE to be equals to R0 if and only if RE is being evaluated as epsilon S equals epsilon F and is equals to what? 0. And is equals to 0. If they are both equals to 0, what does that mean? That means there is no intervention. And if I now put these two control parameters to be equals to 0, that means I will have 1 minus 0 that's 1, 1 minus 0 that's 1, times what? Times R0. And that also brings us to the fact that RE is less than or equals to R0. RE will be less than R0 when there is the presence of those interventions. And it will be equals to R0 when those interventions are absent. Your interest is to model the effect of vaccination on the dynamics of COVID-19. That means you must be able to capture that effect of vaccine in your model. And when you are now computing R0, you will not be computing R0 again. You will be computing RE. because there is a level of protection in the population already. Okay, so thank you.
I'm supposed to be the next person, but I've been able to get answers to my question looking critically on the board. So I was actually disturbed by the force of infection while differentiating with respect to. I was disturbed with the partial. I was disturbed with the force of infection while we are differentiating F. Okay. So you know there is an addition connecting asymptomatic and symptomatic. So. Okay. I've forgotten that when you are differentiating, it's a partial differentiation. Yes. So at some point, I was wondering that where did I go? On
the last slide, when where we were able to see the final value for R naught, how can we proceed from that point if R is less than 1 or greater than 1? We have square root of values, yeah.
So that's now the beauty of quantitative analysis. Okay. You know, all those parameters, they are symbolic in this case now. But maybe you are able to get the value for those parameters either from literature, if you still want to do those exercises, or you are able to train your model with data and estimate those parameters from fitting based on the data you have. You know, like Mr. Mogoduri mentioned the other time, if you have COVID-19, we can establish the recovery rate. Recovery rate will be established, alpha A, alpha S, based on the biology of COVID-19. The incubation period is between 5 to 14 days. A symptomatic person will need intervention, isn't it? Because nobody gets recovered naturally due to COVID-19 in reality, except for asymptomatic. So that means we expect the recovery for symptomatic to be higher, isn't it? Okay, so we will know this from literature, we will know the recruitment rate. But those ones that we may not know are the effective transmission rate, like beta. And all this will come from where? From your fitting process. Maybe in the course of your fitting, you subject your model to fitting. At the end of the day, maybe the data is something like this. You know, if in your fitting, you will also have your fitting outcome, maybe behaving like the data also. At the end of this fitting process, you will obtain the numerical value for other parameters that you are fitting. So if you now look at those parameters, and you substitute it into your alpha S as value, what is the numerical value? Maybe 2 point something. If you get it to be 2.5, that means the disease will persist, isn't it? Of course. But if your R naught is now equal to 2.5, if you take, for instance, we have 1 minus Federal epsilon F, 1 minus Federal epsilon S, R naught. This one is now what? 2 point something. How much effort of this do we need to put in place so that the result here will be less than 1? It will not give us insight that we must make more campaign or enlightenment on people to do social distancing, so that if there is a certain coverage of people using the face mask, observing social distance, in the long run, we forget about COVID-19 causing havoc in the population. I hope that.
Thank you, sir. Thank you.
The issue of immunity is a very complex thing. So now there are models that came up with prediction about natural immunity and all that, but the challenge was that immunity is heterogeneous. Like as we are in this place, our level of natural immunity is not the same, because immunity is a function of genetics, it's a function of your nutrition level, you know, a lot of so now that some people, do you know that there are some people that they cannot have HIV? There are some population, even if they sleep with HIV patients, biologically they can't have HIV. Are you getting me now? So if you compare yourself with such people, so that's why it was advised that in the long run, when they saw the model, that the prediction about natural immunity, the model predict that, less people in the population will have natural immunity. So they now say that, now instead of saying that we should depend on natural immunity, since it's a heterogeneous thing, let's find a vaccination. Vaccination induce. Now, one thing about vaccination is that you are vaccinated does not mean that it will confer immunity. That's the challenge. Now, vaccination can also cause complications. But to a large extent, the study came up with the fact that now if people are vaccinated, there is high possibility of boosting their immunity due to the vaccine. Not natural immunity now, due to the vaccine. So for COVID, the model predicted that a large number of people will be saved due to the vaccination than when you say that we should play natural immunity. You understand what I'm saying now? So, and that was why they concluded on using a vaccine as a control intervention to avert many cases of COVID in many places. You understand? So we can still model and put natural immunity, but what the model predicted was that because the issue of natural immunity is a complex thing, so we cannot completely depend on that for everybody. So there is need for us to, even some people collected the vaccine, they still needed to collect a booster. Yes. Because the vaccine wanes or some people had issues with it and all that. So I think that's the idea from what he was trying to explain. Thank you.
Thank you, Prof. Thank you, sir.
So it's like you are saying that you have, that's what, like malaria now. If we can bring malaria to less than 1, does not mean that you should fold your hands. Now, there is what we call internal heterogeneity and external. Now, when you have dealt with internal heterogeneity in terms of what goes on within, now when disease has been eliminated, don't go and fold your hand. There must be continuous surveillance. In the sense that there are border entry, there could be imported immigrants, imported diseases through infected immigrants. Are you getting what I'm saying now? So that your R naught is less than 1 does not mean that you fold your hands. A lot of things can still go on. And then when you say R naught is less than 1, now it's also location dependent. Now, R naught is less than 1 in what place? And then the R naught is less than 1 is also questionable in the sense that now, what will have made R naught to be less than 1? It means that, are you saying that there is no control intervention? Do you understand me now? When you say R naught is less than 1, it means that have we not put any control? You must be able to answer that. Because if you have put control, it will no longer be R naught. It will be RE. Are you getting me now? So you must be able to answer, have you put control intervention or not? I don't know what the situation you are. So which situation, can you tell us the situation that you are actually addressing? Which disease? Measles. In what place? In Ondo State. So you cannot say R naught, you can say RE, not R naught. Effective reproduction, because you have introduced intervention. So you are talking about RE now, not R naught, because R naught is always, just like, can you describe it there? The curve for R naught, when you are supposed to calculate R naught. Put the graph, show the graph. When you are supposed to calculate R naught. Yeah, that's where you can calculate R naught. So if the disease has started dropping, you don't talk about R naught, you talk about RE, because it means that there must have been intervention that has been put in place. So we call it controlled R naught. Controlled R naught. Okay? Yeah.
Thank you, sir.
All right, thank you so much, Dr. Afis. We are delighted to have you. So straight away, we'll go have our lunch, and we'll return to the next sessions. So this is 40 minutes past 4, and because we need to be able to at least do one or two things before we leave, at least we want to look at some hands-on on her before we go. So if we can take 30 minutes to do our lunch and then return afterwards, that would be a good one. All right. So please let's go. And then, okay, thank you, Prof, for reminding me that. So when we come in, what comes first is the FGS exhibition, and then just for somebody to show us what she has done in FGS, which is genital schistosomiasis, and then we go into the HAR class, and let's see how far we can go after that. So let's go for our meal now. In the next 30 minutes, we'll be back. That means by 4:45, we'll be back. Now, even though on the banner we said 10 to 5, but we all know that we didn't start 10 as we're supposed to start. So you may permit us to push it a little bit further. Maybe around 6 we'll be done. All right, thank you. Let's go for our lunch.